In this video, we will talk about what countable and uncountable sets are. Okay, so if a set S is finite, or it has the same cardinality as the positive integers, meaning if there's a bijection between it and the positive integers, it's called countable. If it does have a bijection with the positive integers, it's called countably infinite. Okay, if it's not either of those, the set is called uncountable. So in this video, we'll give some examples of countable sets. In a later video, we'll show an example of something that's uncountable. So it turns out that the non-negative integers is countable. We've actually showed this kind of informally before. Let's revisit that. In the first video of this section, we found a bijection that takes us from this set to the positive integers. Because all we do to get from this set to the positive integers is we just add 1 to all of them. So the formula would be f of n equals n plus 1. Okay, and if there is a bijection going that way, that means there's an inverse function going the other way. So to get from any of these positive integers to anything over here, we just have to subtract 1. So the inverse formula would be n minus 1. Okay. So that's nice. So when I want to establish something is countable, I have some flexibility in terms of, well, do I do a bijection in this direction or do I do a bijection in the other direction? Sometimes the problem will specify which way it wants, but if it doesn't, I could go either way. Okay, so here's a key idea. A set S is countable if its elements can be written as a sequence or a list systematically. So we've seen this a little bit already in the last video, but we'll see it again in this example. So I want to show that the set of all integers is countable by finding a bijection between the positive integers and the integers. So this will show, in essence, that the positive integers have the same size as the integers, which is a little weird, but that's kind of been the theme of this section. A lot of weirdness with the sizes of infinite sets. For this example, I don't want you to prove that it's a bijection, but it needs to be clear why it is a one-to-one correspondence. So I don't need to prove it's injective and surjective. Just make it clear that it's a one-to-one correspondence. So as we saw in the last video, to get something like this started, we list out the elements of our two sets. So for z plus, my positive integers, if I list those, I get 1, 2, 3, 4, 5, and so on. And then I want to list the elements of z. When I do this, normally if I list out all the integers, I would go like 0, 1, 2, and so on, and then do the negative integers. You don't need to write that down because I'm going to change it. The problem with this is, if I start to match them up, like maybe I match up the 1 with 0, and the 2 with 1, and the 3 with 2, and the 4 with the next thing. Well, it's unclear, how am I going to get to this side? Like, at what point will I start shifting to this side? I don't have a systematic way of doing this. So it's kind of problematic if one of the lists just goes out infinitely in one direction, but the other list goes out infinitely in both directions when I list it. So let's try to fix that. Let's try to do it so I just list out the integers in one way. So if I try listing them, maybe I start at 0. And then just go like 1, 2, 3, 4, and so on. Well, it's unclear at which point I'm going to start to insert some of the negatives, because I need the negatives. Those are integers. So, okay, this isn't systematically going to list all of the integers. So here's the idea I can use. To make sure I get positives and negatives, why don't we switch back and forth between them? So maybe I'll go 1, and the negative 1, 2, and the negative 2. And then I keep going, 3 and the negative 3, and then so on. And this will make sure I'm systematically getting to all of them. So now I will form the bijection where I map the 1 to 0, 2 to 1, 3 to negative 1, and then so on like this all the way down. So what I need to be able to do now is, find a formula for this bijection. It's clear from the way I'm pairing these that everything in the top set is paired with exactly one thing in the bottom set, and vice versa. So it is going to be a bijection, but I need to find a formula for it. This is a little tricky, because some of these things get sent to negatives, some get sent to positives. So I'm going to use the fact that it's kind of alternating and think about what happens to the evens and what happens to the odds separately. So the even inputs, the ones up here, the evens that I'm starting with are 2, 4, 6. And the odds that I'm starting with are 1, 3, 5, and so on. But let's just establish a pattern here. So 2 gets sent to 1, 4 to 2, and 6 would be to 3, and so on. For the odds, 1 gets sent to 0, 3 to -1, and then 5 to -2. So let's try to find a formula for each of these. So for the evens, well, I can get from the ones that I'm starting with to the ones that I'm ending with just by a simple division by 2. Okay, so I have an idea for the evens. I'm just going to be dividing by 2. The odds are a little bit more challenging. With the odds, I'm going to need 2 steps to get from where I'm starting to where I need to end up. I'm first gonna subtract 1, because that'll get me 0, 2, and 4. And then I'm going to take those numbers, and I'm going to then divide them by 2. If I divide them by -2, I also got to switch the sign. And that'll get me 0, -1, -2, and so on. Okay, so the fact that I need to consider evens and odds separately means I'm going to need a piecewise function. So I'll need something if n is even, and something else if n is odd. If n is even, what my scratch work tells me to do is just divide the number by 2. So I'm just going to take n and divide it by 2. And when n is odd, I take n and I first subtract 1 from it, and then I divide the whole thing by -2. That's what the scratch work has shown us in the 2 cases. So this is a bijection from z plus, I was starting with z plus, to z, to the set of all integers. Therefore, this proves that z, the set of all integers, is countable. So, in other words, in a sense, the set of all positive integers and the set of all integers, they have the same size. Okay, so in the next video, we will talk about the rationals and show that they are countable as well.